Hello guys, this is Hayden Bird, and this is Physics 2, Lab 5, Magnetic Braking with Faraday. The purpose of this experiment is to understand how Faraday's law is applied to real-world situations and to create a computational model of a magnet interacting with various conductors. This will allow us to answer the question of what happens to the dynamics of a system when you flip a magnet around, how does the total and time tube of your real-world system compare to that of your computational system, how might the computational system be more accurate, and what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet. The physics principles used in this experiment is Faraday's law, which is the integral of E times dl, and the variations of Lenz's law as I have pictured below. A brief rundown of the results is that the computational model took roughly 1.03 seconds to fall, while the experimental model had an average of 0.94 seconds to fall. Lenz's law allows us to visualize and understand the effect of a magnetic field on an electric current, and Faraday's law establishes a relation between magnetic flux and electromotive current, and this is why these specific models were used in this experiment. I hypothesized that the experimental and computational methods would differ, as the computational method does not account for the magnet potentially rotating or being affected by air resistance on its path down. And regarding the materials on the experiment, you can see them to the right. I identified the system in this experiment as the roll of aluminum foil and everything inside of it, including the magnet, and the surrounding is the atmosphere that the aluminum foil is placed in, which includes the current and magnetic field of both the aluminum foil and gravity/air resistance that comes with living on Earth. Here are the listed initial conditions used for this experiment, which will be explained later in the glow script code. Regarding the actual experiment, we have two images right here. The left being the graph showing the relationship between the velocity and time of the computational model. The velocity increases in the negative direction, then decreases in the positive direction before hitting terminal velocity. And pictured to the right is an image of the aluminum foil magnet used in the experimental model. Potential reasons for discrepancy include the systematic error of the magnet being affected by air resistance and observed to rotate on the way down to the ground, skewing the direction of the magnetic field. And other random sources of error include potential human error in measuring the precise time it took for the magnet to hit the ground, potentially skewing the data for certain trials of the experimental method. Here's the first part of my code for the glow script. The constants were derived from the experiment and measurements from the initial conditions. The sample code in combinations with the values from the initial conditions helps us to simulate the tube of aluminum foil. The second part of my code includes creating a bar magnet, which is derived from the initial conditions, and allows us to simulate a magnetic field in this experiment. And the function you can see listed towards the bottom half is creating a magnetic flux to impact the electromotive force and current. For the third part of my coding, we have the simulation loop, which allows us to predict and visualize the motion of current in the magnetic field. And the last bit of the code is establishing locations, which helps us understand where/what the forces are acting on and measure the distance between the starting point and the ground and to time when the magnet hits the ground. This is the visualization of the computational model. We are assuming for this case that air resistance is neglected, and as you can see, the magnet in the picture depicted by the red light has hit the ground, the fall path being mapped by the gray tube in the picture. I was initially correct that the two models would differ based on air resistance and torque impacting a falling object. However, I did not expect the velocity to slightly slow down before reaching terminal velocity based on the laws of gravity, which has been shown to happen in the computational model graph. Lastly, we have some discussion questions to answer for the video. The first question asks, what if the resistivity of the conductor was reduced as close as possible to zero, and how would this affect the dynamics of the falling magnet? Faraday's law outlined an inverse relationship between resistance and current, meaning lower resistivity would cause a higher current. The change dynamics would imply that the fall time would be slower because the induced magnetic field would be higher than before. The second question asks, what if holes or slots were cut into the tube, and how would this affect the ring currents in your model? The addition of holes and slots in the aluminum tube would result in less quote-unquote rings of aluminum atoms that would have an induced current. There would be, as a result, less current, and because of this, the magnet would fall faster than normal because there is less force attracting and repulsing the magnet. Thank you for watching my video. Please be sure to like, share, and subscribe.